This is a video presentation of a senior design project at Grove City College, sponsored by ASHRAE. The title of our project is France Lite, and on this team is Josh Brown, Sam Calhoun, Aaron Hughes, Jesse Litzenberg, Connor Monahan, which is myself, Noah Stewart, Sarah Trinkle, and we are advised by Dr. Barty. Our project deals with primarily food dehydration. Food dehydration is done today through forced convection. This method uses an airflow at moderate to high speeds to be passed over food until it reaches a desired final moisture level. The process of moving conditioned air at high speeds leads to a high power consumption. To help limit the overall power consumption of the food dehydration process, alternative methods are being developed. One of these is electrohydrodynamic drying, or EHD for short. EHD uses an electrode suspended above a grounded conductive plate. The electrode is supplied with a voltage anywhere from 8 to 30 kilovolts. This creates an electrostatic field that disrupts the surrounding air by the passage of electrons to the grounded plate. This creates a secondary airflow in the system that increases the overall heat transfer coefficient. Even though this is a very high voltage, the electrode carries a very low current. The power supplied to the electrode has a current cutoff actually of 300 microamps. Due to the system having a high voltage but very low current, the total power consumed is under 2 watts of energy for a normal test. EHD is to be used in conjunction with forced convection. The airflow created by the electrostatic field is the primary factor in the dehydration of the food. Because of this, the main airflow of the dehumidified air can be reduced to up to 90%. This changes the role of the main flow from being the main driver for the food drying to now just keeping the surrounding air at dry conditions as the EHD dries the food. So a little bit about the project history. This is a project that originally started at Oniris University in France, where you had a forced convection chamber and the electrostatic EHD system. And then during the academic year of 2015 to 2016, an electrical engineering senior design project was tasked to replicate the electrostatic portion here at Grove City College for research. During the year after that, independent studies were done on this system to troubleshoot their design to make it research ready. And then that's where we come in. During this academic year, we were tasked to replicate the forced convection chamber in conjunction with the EHD chamber. So this project deals with 2 different tests. The first being as a water loss test. This is kind of what I described on the previous slide, where you have a conductive grounded plate with a food sample on top, and you're measuring the moisture loss. To measure the moisture loss, we're using a mass balance towards the bottom of this slide. And then on top of that, you can see the grounded conductive plate. On this plate is where the food sample sits, and the electrode is suspended on top of the food sample. So we are testing the moisture loss due to EHD in the forced convection chamber. The second test is a heat transfer test. There's a bunch of information on this slide that I'm not going to get into just for the sake of time, but this is how the heat transfer coefficient is calculated due to the different fluxes. To measure the different fluxes, conduction, convection, and radiation, there are a series of sensors centralized around the hot plate. As you can see on this slide, there's a grounded hot plate towards the bottom. The electrode is suspended on top of this hot plate. And then this grounded hot plate is supplied at a constant voltage till it reaches a constant temperature that is measured by the infrared sensor above. In our test, we were doing 50 degrees Celsius. And the meaning for this test is to measure the heat transfer coefficient as the EHD is turned on. You can actually see the temperature decrease of the hot plate just due to EHD alone. And with that, I'm going to pass it on to Sam, who's going to talk about the design.
On the left, you can see a diagram that we started with for this year. We knew that we needed a dehumidifier, a chiller, and a cooling coil that will push dry room temperature air to an EHD chamber that we would also build. On the right, you can see a render of our finished product. This is a little bit more complex due to the design requirements for this project that I'll go into now. So first, we needed to create a system to change between the water loss and the heat transfer tests easily and quickly. We also needed to create a contained environment that was both airtight and would protect the outside environment from the electric field that was created by the EHD apparatus. We needed to create consistent air properties, be it velocity, temperature, or humidity, so that we would limit that variability within the testing procedures. We wanted it to be easy to transport so that it could be moved between rooms in a building or even between buildings based on the changing needs of the college and what rooms are available. We needed to be able to adjust the electrode configuration so that the experimenters could test for the optimum electrode placement for the maximum EHD effect. The apparatus in France cost tens of thousands of dollars. We received a gracious $5,000 from the ASHRAE undergraduate program equipment grant. We also received another $1,500 from Grove City College for a senior design project. This is still much less money than the program in France had, so we also had to deal with that challenge. At the beginning of the year, we knew that we needed to buy the meat of our project, which was the basic air handling system. We purchased a dehumidifier, which is a desiccant dehumidifier. Essentially, it heats up air and pushes it through a chemical desiccant wheel, which absorbs the moisture. It then pushes that warm, dry air out of the outlet and then expels the moisture from a separate port. The chiller had the exact amount of cooling capacity that we wanted to have, which was about 500 watts. And the cooling coil itself is designed to cool greenhouse air, so it fit our needs pretty well. The drying chamber itself, we constructed it using polycarbonate sheets. We initially envisioned this project to have a clear drying chamber. However, we realized later on that it needed to resemble a black body so that we could complete our heat transfer calculations. So we ended up covering it in a black vinyl sheeting. It's sturdy, so it has outside corner brackets as well as inside 90-degree angle brackets so that it isn't flexing as polycarbonate tends to do. It has inlet and outlet ducts. The outlet duct at this point feeds directly to the outside through a window. The doors are hinged and they have a magnetic locking mechanism, and all doors and corners are sealed with silicone so that no air escapes. The electrode rods and rails are constructed using a 3D printed ABS plastic, and electricity is fed through them using copper. The rails are powered using a copper plate that's connected to the power supply. And then there's a copper loop at the bottom of each rod, and there's a copper rod going up through the core of each ABS plastic rod. From there, as you can see in the picture on the bottom left, one can complete the connection by stringing a wire of copper between two electrode rods. And when power is sent through that wire, it creates a voltage differential between that and a grounding plate below. The water loss test plate consists of a neoprene film on which the grounding plate and the food sample sit. This allows the weight of both of those to be measured by a scale below the drying chamber, which will read the differences in mass over the course of an experiment as the food is losing water. On the right, you can see the heat transfer test plate. It essentially gives a place for the hot plate to rest and it provides a similar electrode configuration design. Both plates have Velcro strips on each of the four sides so that there can be multiple electrodes placed on each plate. And each plate is the exact same size, so it fits in the same slot of the drying chamber. And now I'm going to turn it over to Noah, who's going to talk a little bit more about the design.
From the other parts of the design is the two boxes you see are the high-powered electrode high power voltage source that powers the electrode, as well as the blue and gray box, which is powering the hot plate. And so the black box powers the electrode, and that usually ranges from anywhere from 8 to 20,000 volts. And it's being controlled by the system that Sarah will talk more about in the coding that can ramp up, and we can control it specifically to where we want it over any sort of period of time, from a 5-hour water test to a 12 to 14-hour heat transfer test. And it can ramp up anywhere between 8 to 20,000 volts and stay at any of those times for as long as we need them to be. And the hot voltage plate, the hot plate box is powering the hot plate, and as well as kind of just set to a certain temperature. And we use that for the heat transfer test, which is as Connor kind of talked about, or Sam kind of talked about, the hot plate is being measured by the infrared sensor, which is overhead, measuring the different temperatures of the hot plate. The graphic you can see on the right goes into a little bit of where the voltage is being placed in the EHD system. The red wire attached to the orange slider is powering the copper railing, and that's how we get the voltage from the high power voltage source to the electrode. And then, as you can see, the black wire is grounding the conductive plate to allow for a current to flow through the air between the electrode and the conductive plate. The next thing, sensors, was a big part of this project. While a lot of it was mechanical and had a lot of the EHD system and the air handling system, the ductwork and all that was a big part. A whole nother aspect that Sarah worked a lot on was the sensors. And we have a lot of different sensors involved in the whole thing. Some of them include the humidistat for the dehumidifier, so we can control the humidity that we have the air coming out of the air handler. And we pick that humidity and account for the fact that it's going to change when it goes through the coil to be about 30% when it goes over the EHD system. We have a temperature and humidity before and after the chiller. It measures the air, so we have an idea of how the chiller is affecting the air, and we have a strong sense of what the air is, what the quality is of the air as it goes across the drying chamber, and also velocity entering the chamber. For the experiments, the other sensors, we include the infrared sensor, which I briefly mentioned, which measures the hot plate temperature, as well as an ambient air thermistor and a wall temperature thermistor. Both those sensors are specifically used for the calculation of the heat transfer coefficient when we do heat transfer tests. Next is Josh talking about manufacturing.
So for the manufacturing of the design, it started in the spring with the beginning of the construction of the drying channel. We had several parts that were 3D printed beforehand, including the end caps and the test and the rail system that we had previously designed. Then we had to construct the basically outer sections of our device, which we cut to size using a circular saw. And then with things like the ends and the doors, we then proceeded to put them into the fall doll in order to get the required accuracy to match our 3D printed parts, such as our pinions and rack systems, and so on and so forth. So we had other things also constructed outside of this, but we also had to drill several holes in each of the sides of the drying channel in order to adjust for the support brackets. And also we had to drill a couple holes in order to actually attach the legs, which were also painted as well. And we also had several other things that had to be designed that didn't actually touch our drying channel, such as our coil stand and our shelving units. We also redesigned our door latch as the original version needed some corrections for better security. We did this for the coil stand, we proceeded to mill out 80/20 and then attach them together using support brackets. For the shelving units, we drilled holes in our actual cart. We added a couple of pegs and threw a shelf on it. And then there was also another shelf added for our computer stand. And that is pretty much the manufacturing. All right. And next will be Sarah talking about the sensors.
Another large part of our project this semester was creating the application for the design. Now, the current application for the system is shown here. It is a graphical user interface that is easy to use. Originally, the sensors for the tests were shown on the main page, as seen on the left. You can see that on and off is either green or red, depending on the sensor's validity. There's also readings for all of the green sensors that show the user the current readings for the system. This semester, the additional 5 sensor readings were added to the interface, as you can see at the bottom of the sensor reading list. In order to do this, the application code needed to be changed. In order to add code to the current system, there were a few different requirements. The code is written in Python 2.7, so in order to run it, the computer needs to have Python XY and Python serial for version 2.7 rather than version 3. Additionally, to obtain any readings from the sensors, the system needed to have the LabJack library installed, specifically the U3 library. This is because all of the sensors in the system use a LabJack U3, which is a DAC unit that gets the readings from all of the sensors. Now, to actually edit the code, I needed to be added to the Bitbucket repository. Now, this is a website that holds all of the current and previous versions of the application, and this allows anyone that has access to it to make changes. And now, in order to actually make the changes, they have to be created in the code. They have to then be committed and pushed onto that remote repository. This is done using an application called Gitkraken. This is essentially version control. This allows users to change the code, push them to the remote repository, and see the changes on the application. As you can see on the screen, the changes are all pushed onto the code and by different users, and no issues are caused by this. Now, the main portion of the coding was integrating the sensors. The sensors of the old system used a LabJack U3, as stated. However, there were no more ports on this LabJack in order to add the additional sensors, so a second LabJack U3 needed to be ordered. Now, the first additional sensors we obtained were the EI1050 temperature-humidity probes. These were to measure the temperature and humidity before and after the coil. The operating range for these probes was between -40 degrees Celsius and 120 degrees Celsius, and from 0 all the way to 100% relative humidity. Now, the accuracy of these probes was from 0.5 degrees Celsius and plus or minus 3.5% relative humidity. Now, these probes were specifically useful in our design because they were compatible with the LabJack, meaning that there is a library of functions in order to get these readings. Additionally, they would work well with our system because the temperature and humidities we are reading are well within the operating range. And as for the accuracy, since we want a relative humidity of under 30% in the drying channel, and we expect a relative humidity of around 20%, the plus or minus 3.5% is no big deal. Now, these probes are connected to the LabJack. They are powered by the LabJack through a digital output and the ground. This provides about 3.5 volts. Then the various wires are connected to digital inputs on the LabJack. Now, using the library functions for these probes, the user is able to obtain the readings for temperature and humidity at both locations. The next sensor we added was an air velocity transducer. Now, this was a Freudian probe FP132A. It ranges from anywhere from 0.2 to 12.7 meters per second, and its accuracy is about 0.05 meters per second below 1 meter per second velocity. This also has an accuracy of about 5% after this calculation. Now, this sensor was a little more complicated since it is not directly compatible with the LabJack. However, we were able to power it through the LabJack using the ground connected to the LabJack, as well as connecting the power to a volt port on the LabJack, which provides 5 volts. Now, it has an analog output wire on the sensor, which is connected to an analog input on the LabJack. In order to actually get the velocity from the sensor, the LabJack reads the voltage that's being outputted and puts it into a calculation. This calculation was provided to us through the air velocity transducer's manual. Now, once put into this calculation, it converts it into meters per second, and this is shown to the user in the application. And now I will take it over to Connor to talk about the data.
Okay, thank you, Sarah. And now I'm going to talk about some of the tests that we were able to run. One of the first tests we did were 2 1-hour heat transfer tests. Here is a graph of the voltage, which is pictured in yellow, and then the 2 surface temperatures of the hot plate over time. This was a 1-hour test like I said before, so the x-axis is a 1-hour time span. And then we used a voltage scheduler to go from 10 kilovolts all the way up to 16 kilovolts. One thing to note is that the hot plate started around 46 degrees Celsius, and then at 16 kilovolts, it went all the way down to around 36 degrees Celsius. So this is just due to EHD alone. This original 46 degrees was when the forced convection was being blown across the food sample too. Here's kind of the same thing, but this is for the heat transfer coefficient. Again, the yellow bar is the voltage over time, and then the orange and blue lines are the heat transfer coefficient. So one thing to note, it went all the way up to around 40 for the heat transfer coefficient. And another thing to note about these results is that it's symmetrical around the 16 kilovolts. So that is cool because we're getting consistent results. Another test that we were able to run is 2 14-hour heat transfer tests. Here are 4 different graphs. These were done in 4 days apart. So on the bottom of the screen, you can see the surrounding temperature. They were about a 1.5 degrees Celsius off from each other overnight. So this was a 14-hour test, like I said, where we varied the voltage anywhere starting at 0, so we can get a base reading, all the way up to 20 kilovolts in increments of 2,000 volts. Along with the 2 heat transfer tests, we were able to conduct 2 water loss tests. For the water loss test, we used 2 potatoes as our specimen. Here's a graph showing both water loss tests. The blue line is the first test and the orange line is the second test. The starting masses were a little bit different. The first mass started at 160 grams, but the second test started around 210 grams. As you can see, the weight decreased over time, just like you would expect, and it's almost an exponential decay because it starts linearly, but as the surface of the food and subject starts to lose moisture, it starts to decrease, as you can tell, the somewhat curvature that we get around the end of the graph. And now I'm going to pass it over to Noah, and he's going to talk about our finances.
As Sam mentioned earlier in the design slides, one of the major goals and constraints of this project was the financial aspect of it. And being able to make this EHD drying system under budget was crucial to what we're trying to do here at Grove City. And so we had a very strict budget. We had $5,000 funded by the ASHRAE undergraduate program equipment grant and $1,500 supplied by Grove City College and their Senior Design Fund. And with that money, we were able to purchase and build everything that we did with the drying system. Now, this was super important because, like briefly mentioned, the system that we're replicating that's done in Onneries, France, is worth tens of thousands of dollars. So to do it for over half the price was super important to us and critical to what we're trying to do here at Grove City. So a breakdown of the costs is shown next. The total cost of the project came to $5,924.55, so just under $6,000. So we were able to stay under budget by almost $600. As far as planning goes, we were required to try and get most of our stuff bought before the semester started. When we were going to build, we were able to get 81% of our materials ordered in the fall semester, which is a testament to our ability to plan for this semester. So if you can look at the chart at the bottom, this is our Pareto chart talking about some of our expenses, breaking it down a little bit farther. As you can see, the first 2 boxes, the desiccant dehumidifier and the chiller, were by far our 2 largest expenses. And those 2 things were mostly what the professor running the experiment was able to get the grant from ASHRAE. Those were the main materials in the drying chamber, and what most of our budget went towards. The rest of the budget, which you can see these smaller bars going through, were mostly the building materials for the drying chamber, including anything from the vinyl sheet to the nuts and bolts, the corner brackets, the polypropylene sheets that built the drying chamber. That's where a lot of the meat of the items were bought. And the other thing that took some of our budget was the sensors and the lab jacks that we had to buy for the coating and the coating that Sarah was working on throughout the project. So that's just a breakdown of how the money that we received from ASHRAE, as well from the college, was spent moving forward with this project. So next is Jesse with the future of the project.
All right, so does the system work? As of right now, it does. Barring any serious complications, the system's working fine. We were able to run both the water loss test and the heat transfer tests pretty much right away. We did have a problem with the water loss test where the scale was being affected by the new airflow that was introduced to it. So to combat this, we used heavier test samples, and that seemed to have fixed the problem. We might end up using a thicker plate and a smaller test sample to still overcome this problem. Goals met. The system is cheaper than the one used in France. The one in France, as was previously mentioned, cost tens of thousands of dollars, whereas this one has only cost us just under $6,000 to create. As I mentioned, we can do both tests, and the results have been great. Also, the modular design that was required from us was achieved. We're able to move this system anywhere throughout any of our academic buildings. The two carts come apart when you detach the flexible duct in between the chiller coil and the drying chamber, so they're completely independent in movement. We achieved the adjustable electrode configurations that we wanted to, as was mentioned earlier. There's plenty of storage space on this, so whoever is conducting experiments can add more to the system, or whatever they need the space for, they can use it for. In the future, there's a few things that need to be tweaked and made so this system is absolutely perfect. One of these things is making the channel better emulate a black body. It was brought to our attention that for our radiation calculations, the channel probably should be a black body. However, this was very late in the process, so we didn't have time to tear it apart. So as was mentioned, we covered it with a matte black vinyl sheet. And then also we wanted to be able to pretty much start the system and then remove our hands from it and it go and stay at steady state. It's not quite there. The sensors are in place for the control system, but the coating needs to be tweaked a little bit. But doing that would really take this system to the next level. And with that, we want to thank you for listening to us and taking some time to be here. Are there any questions?
We would like to thank the generous support of ASHRAE, Grove City College, and the Grove City College Mechanical Engineering Department during the duration of this project. Also, we would like to thank our advisor, Dr. Eric Barty, and Mr. Jim Peisch, Sam Tascarella from the Pittsburgh chapter of ASHRAE, Mr. Scott Gillette, and Dr. Michael Have from Oni Reese University.